Alright, as I said in the last video, in this next section we're learning how to handle forces that are distributed instead of just point. You use snow on a roof as a good example. So we're going to talk about that in more detail. Another example would be wind blowing on a surface area. Water behind a dam. There's a lot of ways, a lot of cases that this will be applicable. And what we'll do is focus on a beam, and then this will be where other courses take off, mechanics of materials, for example. So imagine you've got a beam, and imagine that it has a load on it. Like we said, it might be snow, it could be a lot of different things. It's distributed as a function of length. We're going to call that load as a function of length W of X. So it'll have units force per unit length. So newtons per meter, pounds per foot. And so the way we'll calculate, since it's a function of X, what we'll do is we'll get the total force that this would be on the beam by doing the old calculus trick. We're going to take a small piece of the beam, assume that what's on top of it's a constant, and then the W will be the height, and then if we multiply that times the area, we'll have our force due to that little piece of the load. So it has width dx, height w, and then if we add those up, let the size go to 0, that will become an integral. So the total weight due to this distributed load, W of X, or the total force, is integrate W dx. And that's effectively, W dx is essentially the area. So it's basically the area. So if we have a nice geometric shape, like a rectangle or a triangle, then we can just use the area formula. If not, then we'll have to do this integral W dx. Now, if we're going to figure out, for example, we need to take the moments about O to find a response, then what we'll do is we will say, well, we'll again take a little piece of our force, piece of our load function with dx. It has force dx times w. Multiply that by x to get the torque, so xdf or xw dx, and then add those up along the beam, and again let the size go to 0. That becomes an integral. So the net moment of that force about O would be integrate x times w dx. And then we're going to replace that with the equivalent. We'll replace our distributed load with a point load that has the same total effect. We'll put a force there that has the total weight, the integral of w dx, and then we'll put it at such a place that it'll have the same moment about O, x times fr. Now that's going to turn out to be at the centroid. And so that's the reason we learned how to calculate centroids first, because if we know the shape and we know where the centroid is, then that's where we'll put it. And so these two will be equivalent. Sort of like doing series and parallel resistors, right? We're going to find a mechanical equivalent to the real one that'll help us, aid us in doing our calculations. So we'll have some that are curved that we'll have to calculate. But here's the two standard examples where we won't have to actually do an integral, right? You can, and you'll get the same answer. But if we've got what's called a uniform load or rectangular load, that is the same all the way across, 400 pounds per foot, then the total area is just the 400 times the 10, or 4,000 pounds, and the centroid's in the middle, so we'll put it at 5. If it's a triangle, then the area of the triangle is 1/2 the base times the height, right? So 1/2, the base is 6, that's 3 times the height. 3 times 600 is 1,800, so we'll put it at 1,800. Remember, it's 1/3 of the height measured from the base. So 1/3 of 6 is 2 measured from the right end. So in other words, we'll put it at the centroid. We'll use the area and the centroid and replace that, and then we can calculate the responses at the ends with these equivalents. So here's an example. we've got a linear load, we would call it. It goes from 1,500 Newton per meter to 4,500 Newton per meter. And we want to find the response at A and B. So what we'll do is, what he does, there's more than one way to do this one, but what he does is I can do that with two triangles. The upper triangle and the lower one. It's got 1 and 2. So the lower triangle has an area 1/2 the base times the height. So it's got a 1.5 height. The base is 6. Half of 6 is 3. 300 points, 4.5. So the area is 4.5. For the other one, we've got this triangle, half the base times the height, so the height would be 6 again. The base would be 4.5, so it would be 3 times 4.5 is 13.5. You add those up, you get 18.5, which is the area. I mean, we could also do a triangle on top of a rectangle. So you get an 18.5 total area. Where are the where's the centroid? Well, a third of the height measured from the base. So a third of 6 is 2. That's the base on this one, so it'll be at 2. The other one, a third's still 6, so they have the same height, but the base is over here, so it's actually 6 minus 2, which is 4. Then you do your product of each, add those up, and then you divide this one by this one, which apparently is 3.5, and you'll get where to place it. So you put the 18 here. Where do you do it? Well, you take that and divide it by the area, and we get that. And so now we can use those to find the moment about, of course, the moment about A, we can now do this way using this. So it'll be, if we have responses at A and B, I didn't really draw the free body diagram. We have up forces at A and B. Take the moments. We'll have 6 times B for that one, 3.5 times 18 for that one. You saw for BY. Take the moments about B. You'll have 6 minus 3.5, 2.5 times 18 would be positive, and you'll have 6 times A, and then you can find AY. So by replacing the distributive load with the single load located so it has the same exact moment, will then let us find the responses. All right. Well, I'll do an example and post it up also.